Morning. I guess all of you have been enjoying this FDP until this point, and we have come to the last day of this uh, FDP. And we have with us Dr. Sourav Chakraborty, and he is an associate professor from Chennai Mathematical Institute, and he has been with CMI for the past 5 years, and he was a postdoc at the Algorithms and Complexity Department of CWA Amsterdam, Netherlands, and he also he received his PhD in computer science from University of Chicago. He received his master's degree from University of Chicago and did his bachelor's degree in mathematics from CMI. He was one of the 20 award winners in the Indian National Mathematical Olympiad conducted by National Board of Higher Mathematics. He gave invited talk at Jasdul seminar, which is one of the seminars prized by participants as the most productive academic events on algebraic and combinatorial methods in computational complexity in 2012 and 2014. He has also given talks in the Mysore Park workshop. We are very glad to welcome you here, and he will be giving a session on approximation and randomized algorithms. Thank you.
Okay, since it's a smallish group, I would like to have some more interaction. Okay, so I will start this two session with randomized algorithms and moving on to approximation algorithm. So before I start, I want to ask you what all things have you seen till now, right, in this whatever TP. So let me just tell what I expect you to see, and then we can talk about it, right? So first of all, you have been seeing algorithms, right? So which means that our goal is to solve hard problems. Now, whatever the definition of hard is, right? We will give algorithms for hard problems. And this is our first goal. The second goal is to give good or design good algorithms. Now, what is the meaning by good? Usually, you must have seen good meaning algorithm whose number of steps required is polynomial in the size of the input, right? Which we call as P. P is the polytime algorithm. So class of problems which has polytime algorithm, right? Now, have you also seen this thing called NP? You have seen NP, correct? So what is NP? Then it is non-deterministic polynomial time, or and what are the set of inputs problems? So these are the problems for which we cannot or we don't know an algorithm to find a solution in polytime, but if somebody gives me a solution, I can verify it in polytime. Okay? So the picture goes like this. So if this is the class of all polytime algorithms, of course, NP contains P, and something like this NP sits here, right? And among NP problems, there is a problem of class of problems which I surely think you have seen it, which we call as NP complete. So what are these problems? So these are the problems which we basically don't expect them to be in P. In other words, if they are in P, if any one of them goes down in P, then NP is equal to P. So these are the hardest problem in this class. Now, can you give me an example of a problem here? Traveling salesman problem. Okay, very good. TSP. SAT, okay, SAT, Hamiltonian circuit. Have you heard of this thing called vortex cover? Vortex cover, maximum click. Okay. Good. So let's start my lecture using this set of problems. First of all, okay, all the problems that is here are what are known as decision problems. Now, what are decision problems? So, decision problems are problems for which there is an yes and no answer. Okay? There is no other more complicated answer to that. But as you can expect, not every problem in the world is a decision problem. That's number one. Number two, first of all, we will very soon see not every problem is well determined also. But the other thing that I want to talk about is what is this polytime algorithm, or what is the polytime here? These are what we call as the worst case. In other words, when we say polytime, it means that it is not how the algorithm is performing on an input in general. It is like irrespective of how bad the input is, how can I go? Right? Or for any particular algorithm, maybe any particular input, the algorithm itself does something crazy. And what is the worst thing that can be done? Again, really not necessary. So then what do we do? So let's start with the first problem. Can everybody see this board? Okay. So let's look at the problem 1. It is a very simple problem. Say I have say, okay, I don't know say I have a group of people, okay? Say S is a group of students. Group of N students. Out of which, say, N over 2 are, say, second year. Imagine that this is like a box, okay? I have a box. Half of them are black balls, half of them are yellow balls. Okay? What you can do is that you can put your hand inside and pick one up. Your goal is to pick a yellow ball. What will you do? Just imagine, what will you do? You'll of course put your hand inside, shuffle it very hard, and then pick a ball, right? What does the shuffling do? It is kind of creating a random ball. I am picking a random ball. All I am doing is that picking one ball at random. Okay, maybe that is not yellow, it is black ball. Let's throw it away. Again, put my hand inside, shuffle, pick one more. How many times do I have to do before I get a yellow ball? N by 2 plus 1? Okay, good. N by 2 plus 1 is the worst case. Do you really think that you have to wait for N by 2 times? Think of that you have 1000 balls. Okay, there are 500 black, 500 yellow. Do you think that you have to go and pick up 500 balls before you can pick up one? Yeah, really, if your luck is hopeless, that's what will happen. But you don't expect to have that, right? Here comes the main beauty of randomization. When you do randomness, okay, first of all, how many of you are not comfortable with probability? If you are not comfortable with probability, please let me know. This first, at least half of the talk, plus part will be a bit difficult. So in that case, you have to think of it in a slightly more vague way. but I'm going to assume that you know probability and I'm going full force into it. Okay? So let us pick K balls. I mean K, okay, here I started with students, K students at random. So people who are a bit more worried about how am I picking it, after I pick a ball, should I drop it inside or something like that? Let's do it. Pick a random with replacement. It just helps us to do the calculation easier. Meaning I pick a ball from that box. If it is not yellow, then I put it back. Again, I put my hand inside, shuffle it, pick some other ball. I mean, yeah, there is some probability that that original ball might again come back, but that's pretty low. That's the whole thing. Now, what is the probability that I would not get a single student in the second year? Or in other words, I pick K balls, what is the probability that I will not get a single black ball? What is a yellow ball? Yeah, single yellow ball. Sorry? Can you say? What is the probability the first one is not yellow? 1 by 2, great. What is the probability the second one is not yellow? 1 by 2, right? And they are independent. These two events are completely independent. Whether first one was black or yellow doesn't influence whether my next one is black or yellow. Right? So it is 1 by 2 times 1 by 2. What is the probability the third one is not yellow? Again 1 by 2. And it continues till K times. Right? So this is half over K. How quickly did we move from? Okay. So it was n over 2 to K equals to say 30, I get a probability of 1 by trillion. So K equals to n over 2 to 30. So in fact, it is a reduction from a polynomial time for constant. So in other words, even I am beating the polynomial time bound. I am going even lower. That is randomization. Now you might say that, okay, who uses this thing? I mean, maybe you have already been brainwashed into thinking that, okay, decision problems or whatever, deterministic problems are the way to go. Let me give you a application of this one that you see at least every once a year, maybe more, or surely once a 5 years. How many of you follow politics here? Everybody? No? There's only 2 people? So, how many of you watch the elections? Did you watch the election? In the election, there is something called exit polls. What are those? How are they are doing it? They're predicting, correct? Like, okay, let's say the BJP and Congress. They'll say that, oh, okay, see, BJP is going to win. How are they going to say it? Right? Exactly. So, here, what did we do? Let's come back here. Here, we found one particular thing, right? We will just flip this whole thing a slightly different way. Okay? Okay. Okay, so let's say I have Congress and I have BJP. Now, I say that for a particular election, okay, if Congress gets a vote, I will put it as -1, and if BJP puts a vote, I will put it as +1. Right? Now, what is it? How do I decide? In the original full count that will happen, which will basically be a lot of money spent and a lot of hard work and all those things, they will go to individual people. Okay, so let me call these people to be T1 to Tn. I don't know, it's a huge number of people. Everybody basically has either a +1 or a -1. I've simplified the problem in the sense that I've just said that there's two parties. If there are multiple parties, you can do the same thing. Argument is exactly same. Okay, you have +1 or -1. Everybody casts their vote, meaning in some sense, you can think of in a paper they write +1 or -1. How do you decide who wins? Someone? Huh? Maximum. What does this mean? We sum it up, right? If it is negative, I say Congress wins. If it is positive, I say BJP wins, right? That's a simple thing. But I don't want to go through the whole process. I want to quickly give you a hint. I am a television broadcaster. I want to quickly tell you what is the most likelihood of who is winning. The way we should do is that, as she pointed out, let's just sample some people. Okay? So let's just randomly pick some x1 till xt. Some random people, completely independently at random, x1 to xt. And I check what is the summation of xi. I mean, when I mean summation of xi, I mean the +1 or -1, right? And I will basically answer it based on whether summation of xi is positive or negative. Okay. Now you will say that, okay, this is clearly wrong, right? This is like, oh, what's going on here? I mean, you are not going through the whole thing. It's almost undemocratic. The amazing thing is that this is almost as democratic as you can imagine. Okay, why? First of all, let's understand. So without loss of generality, let's assume that one of the party wins. Okay. So in other words, summation of Pi is equals to, say, R. I'm not putting who is winning and all. R is some value. Okay, it can be P +100, +200, -100, -200, I don't know what. Okay? This is the actual thing. Fine? If I pick, that means, what does it mean? It means how many number of +1 voters? Maybe just for the sake of, well, let me just put some strong numbers here. Okay, so let's say it's +1, +100, okay? It helps to understand it better. Number of +1 voters? Actually, maybe I should slightly make it more ray. Maybe let me call this one as 0.1 n. N is the number of people. So in other words, number of people who is voting 1, how many of them are there? Can somebody say from here? I mean, number of people voting 1 is x, number of people voting -1 is y, x plus y equals to n, right? So that's the total number. And x minus y, meaning if I count with the minus, this comes to 0.1 n. So what is x? Sorry? Half plus 0.05 n. some sense, this is basically kind of modeling the fact that, say, whatever, who is this party? Yeah, BJP wins 55% of the vote. The BJP is winning 55% of the vote. Congress is winning 45% of the vote. Okay, so that's the kind of modeling that is done. I pick up random set of some x1 to xt, and I want to know what is the expected value of this. What is the expected value of this? This is, if you remember, expectation, there is a linearity of expectation. Expectation of sum is the same as sum of the expectation. So this is I equals to 1 to t. So this is I equals to 1 to t. Expected value of xi. And what is the expected value of xi? So this is a random person chosen, right? Random person, completely random. With point, with 55% probability, that means with 0.55% probability, I would be getting +1. With the other, meaning 0.45%, not probability, fraction, I will be getting -1. So the expected value of summation xi is 0.1. So in other words, this number, what will it come out to be? Expected value is, this is 0.1, the t times 0.1. So what is it saying? Let's try to understand here. It says that if summation of pi was 0.1 n originally, I mean there is the actual value, correct? No. Then if I take some t random points, expected value of this summation will be 0.1 t. Note here that t signs remains same. This is positive, that is positive. So why positive? Fraction also remains same. Okay. So, okay. This doesn't end the whole story. I'll soon say why I say this thing. But at least what it says is that if I randomly pick some t things and t can be pretty low, 10. I pick 10 people. Whoever, if I see that, oh, see, there's more people voting for Congress, oh, that means Congress is surely winning. If I say more people voting for BJP, then surely BJP is winning, and so on. This is what the election exit polls are supposed to do. First of all, they don't do, many of them don't understand the math. And secondly, they don't do for another reason. Can somebody say what is it? Is there any proof of here? When I did this expected value of xi, I assumed something. What did I assume? I assume that xi is chosen purely at random. Meaning it can be any one of them, or in any one of, with 55% of them can be +1, 45% of them can be -1, any one of them can happen, and hence this number came. In a country like India, sometimes choosing something uniformly at random is not an easy job. And if I tell you that, okay, pick one person at random from the Kanchipuram district, okay, how will you do it? Most likely will end up picking one from your set of friends, which is possibly not a very unbiased set, right? So here, of course, this independence of the complete pure randomness of the exercise was required. There's one more point that I should mention here. So this is the expected value, right? What does the expected value mean? It means that it can sometimes be 0.2t, sometimes can become t just 0, sometimes can become minus t, sometimes can become plus t, I don't know what. When you sum them up, all of them, then the average comes down to 0.1 t. So when you take 10 people, there is no, as such you should not say like, okay, on expectation I should get this much, is on average, but is it what I see? So if you are confused, let me step back one step and come up with a much more simpler problem here. You have a coin, you toss it 100 times. What is the expected number of times you are supposed to see head? Huh? Sorry? Half of the time, right? 50 times, right? Good. But is it that, okay, half of the time I will expect to see? That doesn't mean that if I toss a coin 100 times, I will see exactly half 50 times, right? I can see it 60 times, I can see it 2 times, I can see it, I don't know what. Any number of times between 0 and 100. Correct? Now the probability that what is the chance that I will see 10 times 100, 10 times head? Is it same as my chance of seeing 49 times head? Which is more? What do you expect? If you toss a coin 100 times, the probability of me seeing 10 heads, is it same as probability of me seeing 49 heads? Probability of seeing 10 is, okay, 10 meaning what? Exactly 10 I mean. Huh? Okay, why? Let's see. Yeah, you're completely right. What is the probability of getting 10? 10 heads. Now, what is the probability I see 10 heads? Can someone calculate? So, what is the probability that the first 10 of them are head and none of them are head? So, x1 to x10 is head, x11 to x100 is tail. What is the probability of that? One by 2 power 10. Okay. So first one is head is 1 by 2. Second one is head is 1 by 2. 10th one is head is 1 by 2. Okay, for 10. What is the 11th one? It should not be head, right? So again, probability of that it is not head is 1 by 2. The next one again 1 by 2. So this is 1 by 2 power the rest, which is 1 by 2 power 90, which of course comes down to 1 by 2 power 100. But that is not probability that I see 10 heads. This is probability that I see 10 heads in the first 10 things. What is the probability of I see 10 heads overall? I had fixed you 1 to 10, correct? Instead of 1 to 10, I could have fixed you 2 to 11. I could have fixed you 1, 3, 5, something, some 10 number of them. Huh? All of them will be 1 half power 100, but how many such chunks can be there? 100, 3, 10. Right? So I can use this one. This is for each one of them happening, and this is the way in which I can pick 10 heads somewhere. I'm going to allocate some 10 things somewhere to have this probability. Okay. Right? I'm doing very simple calculations over here. Now let's do what is the probability that I see 49 heads? If you repeat the whole process again, what will you get? Half power 100, no problem. But now instead of fixing 10 things, I should fix 49, right? So 100 choose 49. Question is that which of these two is bigger? Let's scale down the numbers, okay? Let's scale down the numbers. What about say 10C2 and 10C4 or 5, say? Which is bigger? 10C2 is bigger? You can now calculate it, okay? So 10C2 is 10 into 9 by 2, which is 45. This is 10 into 9 into 8 into 7 into 6 by 5 into 4 into 3 into 2, right? So 3 and 2 is 6, goes off, 4, 2, 2. So it is 4 times 9, which is 36 times 7. You clearly see that this is clearly bigger than this. In fact, why bigger? This number is massive compared to this. Massive. I really mean massive. If you have to plot this number, okay, so if I have a graph, okay, so pick any favorite n, say 100 for the matter, or say 100 or 1000, and I slowly increase. So this is, I mark 10C, 1000C1, which is 1000, right, and so on and so forth, okay, and I keep on marking like that. The graph will be, so if this is 1000 here, this is 500 here, which is the middle one. The middle one will be the highest. The graph actually looks something like this. And where does this sharp turn come up? So what we call here is that if this is n, this is n over 2. If you go up to n over 2 plus square root n and n over 2 minus square root n. For example, if in case of 100, it is 50, 40, 30, 40. Sorry, 40, 60. Between 40 and 60, all the probability lies. In fact, if you toss, if you go for a competition with your friends, have a fun today, okay, have a bet. So let's toss it 100 times. And you say that if you win, if you get less than 30 coins, heads, then you will give him a treat. With almost certainly you will win. With almost certainly. All you need to block is that 30 to 60. That's it. 20 of them. And this number goes slower and lower and lower and lower as you go higher. 10,000, meaning what we are talking about is 4,900 and 5,100. That's it, 200. And you are not going to get anything beyond that. So this is what we call as concentration. Concentration meaning that not only that the expectation is whatever it is, the probabilities are concentrated near the expectation. It is not spread across. In your probability course, you might have heard of these following three inequalities. One is called the Markov inequality, the other one is called Chebyshev inequality, and other one is called Chernoff inequality. If not, go and check it out in the Wikipedia or wherever. These are the inequalities that says that when you toss a coin n times, not only do you expect to see n over 2 heads, you basically don't expect to see less than n over 2 minus square root n or more than n over 2 plus square root n heads. almost always there. It doesn't mean that there is no chance of getting here. There is some chance. It's a very low odds of you hitting one of them. Okay. So that is also the case here. Okay. If this is 0.1 t, then if this one, okay, so most important crucial number in this particular calculation is 0, correct? Whether this expectation is less than 0 or greater than 0. Correct? That's what decides whether I am going to say BJP wins or Congress wins. If it is away, these concentration inequalities will say that with almost no probability or very low probability, say 2% probability, is this actual sum deviate away from it by more than 0.1n, which means that with almost 98% probability, this sum is bigger than 0. That's all I can say. So in some sense, this is very obvious to answer. Okay, if you have two players, okay, or if you have, say, in your school election or whatever, if there are 2% contesting, if one of them has, say, and let's assume that you have 1,000 students, 1,001 students, okay, if 501 students vote for the one person and 500 students vote for the other person, you can clearly imagine that by choosing some sample of them, I will just not be able to decide who is winning. Because there is one person that is finally flipping the whole game, right? It's so close. So in this case, it will become 0, close to 0. But if the thing is that 80% or 70% of the people are going for one and 30% are going for the other, then you take 10 of them. Okay, on expectation, it should be that 7 of them should be going for one and 3 of them going for other. But as long as 6 of them goes for one and 4 of them goes for the other, you're still fine. You'll still be predicting the right thing. So the more the gap between the winning and losing, the higher the confidence level is. So again, when in a proper exit poll, there are some exit polls which are they do a mathematical job of it, and they will say something like the confidence level is 98%. It basically means that. Meaning in that particular constituency, the number of, the Congress is winning by a larger number than BJP, and hence I am guessing it correct. Or in some other thing, BJP is winning by a larger number than Congress, I am guessing it correct. But whenever they two are close, very close, then it is anybody's game. Nobody can guess anything, right? So this is something, there is two things that is important here, again. First of all, number one thing to note, sampling, this is called sampling. Sampling is very powerful. Why? First case, it reveals a lot about the whole population. And when I mean population, I really don't mean always exit polls, but in terms of any data. Okay? Secondly, by doing sampling, you are reducing the size, which means that you are doing a quicker solution. And number three, not only it reveals a lot, but it gives you a confidence. It has a confidence factor to it also. It's not just the expectation, but there is a concentration thing that also happens. So it's not like, okay, I expect to get 50, I can get 100 also, I can get 0 also. No, nothing like that. There is also a confidence factor that you can mathematically deduce. Now this brings us to a very, very important area which is now the buzzword, namely big data. This is big data. You have a data of size 1 million. How do you work on it? You cannot work on it. You sample, work on the sample, and prove something that the sample is actually something like. All the big data results are here. All. So this exit poll is possibly one of the best example of big data. It's a huge 100 crore people in India standing there. You have very limited resources, meaning maybe you can only question 1,000 people in India. From there you have to decide everything. So, I mean, I don't want to go into too much into this exit poll. It becomes a bit boring at some time. But just one thing is that you can see here that I can predict the number of people voting for, or fraction of people voting for Congress or BJP nicely. Question is that can I use it to predict how many constituencies won by which party? The way in which India's election system is done, that comes up to one more level of challenge. And that's where people make a mistake. So if you look at next time you see an exit poll, whatever, you will see that most exit polls will get the percentage of people, overall percentage of say people in India or in a state voting for a particular party, they get it very accurate. Converting the percentage to the number of constituency winning is a challenge. So, okay. If you remember, recall all the algorithms of sorting. Quick sort has all the nice properties. All the nice properties, except one. What is it? No, choosing the pivot is the first step, correct? Question is that what is not the nice property? What do you expect from a sorting algorithm? Marks are better, somebody says quick sort better. Why? Why is marks sort better? Yeah. Worst case running time, right? Okay, running time is one thing. Why is quick sort better? More general, what is the more general means? I don't want to go too much into the details of the sorting algorithm, but the main idea is that other than, so when you are talking about a sorting algorithm, there are various things that you want to take a look at. Of course, one is the runtime. Number two is the space. For example, quick sort uses space log n. Merge sort uses space n. Okay, space not good. Number three, things like, okay, do we maintain the order? Meaning, if I have two objects, both of which, the two files, and you are sorting by the names, okay, or by the name. Nice technique. Problems. Sorry, all the nice properties, like it is very low space and so on and so forth, but it does not have the best of the running time. But still, it is used so frequently. Why? What is the quick sort running time? Worst case running time is order n square. So let's quickly revise the quick sort. Okay, what is the quick sort does? I have this array. It takes a pivot. Okay, this is the worst kind of quick sort thing that can be thought of. I take a pivot. Then I go through this whole array, split it up into two parts. One of them is less than or equal to p, the other one is greater than p. This particular operation, which is order n, plus, so t of this, so maybe call this one L and R, L plus t of R, left and right, right? The problem with quicksort is that L and R can be very unbalanced, meaning L can be 1, R can be n minus 1, for all you know. Right? So in other words, this can actually be, in the worst case, end up becoming order n plus n 1 plus n t n minus 1. This is the worst case. And if you solve this recurrence, you get this is the complexity. Right? But if T and L and R are kind of similar, meaning n over 2 kind of stuff, or n over 3, 2 n over 3, or so on, then what happens? If somehow I could have guaranteed this one as n over 2 and n over 2, then what would have happened? If, this is if somehow it splits up nicely into two almost equal parts, then what would be time complexity? Log n, correct? Then T would be equal to n log n. Now that is the idea. What is the idea? Instead of doing this quick sort, where we take the first element as pivot, let's randomly pick up a pivot. Doesn't have to be in the middle, it's anywhere, okay? Any one of them has equal likelihood of picking up. And then I call it one pivot. And this is called the randomized quick sort. So pick a random pivot. And continue. Okay, the same argument. Pick a random pivot P, you find the left which is less than or equal to P, find the right which is greater than or equal to P, greater than P, and we have the same thing. No difference as such. So this is of course not happening, this is what's happening. But now it's a random. So we can talk about expected runtime. What would be the expected complexity of this one? So the expected value of this T of n is expected value of them, right? So it's the expected value of order n, so which is basically order n, so I don't want to write it here, plus the expected value of T of L plus T of R. Now this is something nice, because as I told you, when you pick something at random, what happens? What do you expect? You don't expect that, okay, every time it should be like super biased, right? 1 and n minus 1. It's like all the possibilities should occur. 1 and n minus 1 will occur, 2 and n minus 1 will also occur, 2 and n minus 2, 3 and n minus 3, all of them will occur. Right? In other words, there is no particular, the worst case doesn't come in. It's like I'm spreading my whole money over all the possible options. Right? No, okay, so basically, what all things can happen? Let's see here. In the actual ordered set, I could have picked any one of those elements as pivot, and I would have got into two different splits. Any one of them would have had the same probability of occurring. Correct? So, and how many of them are there? There are, say, n minus 1 of them, right? And all of them have the same probability. So, all of them have the probability of 1 by n minus 1. In other words, what is the expected value of T of L plus T of R? Let's do it. With probability 1 by n minus 1, I get T of 1 plus T of n minus 1. With probability 1 by n minus 1, I get T of 2 plus T of n minus 2. Plus, continue like that. In other words, this is 1 by n minus 1 summation over I equals to 1 to n minus 1 P of I plus P of n minus 1. And if you see it carefully here, any of the TIs are occurring twice. So this is nothing but 2 by n minus 1 summation of I equals to 1 to n minus 1 P of I. It's just rearranging the whole thing. In some sense, this just says that on expectation, this number should be this, not whatever I wrote earlier, right, which is the worst case, which is T1 plus Tn minus 1. It's not. It is better than that. It's spread across all the possibilities. So the expected value of this one will be order of n plus summation I equals to 1 to n minus 1 P of I 1 by n minus 1. Sorry, not 1 by 1, it is 2 by n minus 1. Okay, I leave you here with this particular problem. Prove that, just say that this does turn out to be twice n log. When you compute this one, when you solve this particular recurrence, you will get En equals to twice n log expected value of En. So in other words, what we are saying is that here is a algorithm, quick sort, which not only has lots of other properties, okay, it doesn't have a worst case property, but in random algorithms, it is as good as any other algorithm, merge sort or whatever stuff, which is 2n. In fact, you can prove the concentration version of this one also, which means that almost never will the running time be more than Cn log n. This is what I was talking about here. Concentration one. Not only the average, the expected value is n log, twice n log n, but it just never goes beyond Cn log n. And this is the reason why every actual applied person uses quick sort instead of heap sort or merge sort or whatever other sort is
it. What is the time involved in picking the random pivot itself?
So what is the time involved? The time involved is not much. It's about you have to have random coin access. You should have an ability of producing a number between 0, 1 and n uniformly at random. I mean, if you are in a RAM model, which we are mostly, then this is not a problem at all. But even if it is not, right? You say, oh, pick up the 10th element as a pivot. You can walk through it, pick the 10th element, and continue working on that. Right? So that is not an issue. Means that do you have a machine to produce a random pointer? Now, this depends upon whom you are asking this question, right? Like I think the people of nowadays, they just type in some random, some kind of software in computer and they produce a random number. The older people, I think I am one of the, at the intersection, I've also used it. There was something called this log tables where you can use them to find a random number. You remember this? There was to be a table for which you can, so that was to be the way of producing a random pivot. So So all this comes down to, can you, so even this analysis, right, this is fact that I'm assuming that all of them is 1 over n minus 1, is based on the analysis that all of them, I'm picking up pivot between 1 and n, all of them are equally likely. So I need a purely uniform random coin generator. Nowadays computers are very good random coin generators, so that's sort of. Yeah. So no, no. So the other way of thinking of this whole problem is that, so what is the average case? Meaning you have been given an input, right? Say I have to say for without loss of generality, let's assume 1 to n. So these numbers are nothing but 1 to n, except that they are not given in this particular order, they are given in some jumbled up order. As you know, in sorting, we don't care about the quantity, we compare, right? So we can, without loss of generality, assume they are 1 to n. Now, one way of doing it is that pick a random one, right? Here, random p and then continue. Other way of thinking is that the input that has been given to me is a random shuffling of this number, and that's the average case. Meaning all the possible random shufflings of, we call it a sigma 1 to sigma n, they are basically the permutations of 1 to n. All the permutations of 1 to n are equally likely to come. If they're equally likely to come, then I don't have to do a randomization. I can just pick this one. So this one now has equal probability of happening any one of them. And again, same as analysis. So in particular, in this particular case, at least I can say that average case and randomized algorithm running time are same. Some other problems, things might be slightly more complicated, and then it all boils down to how you define average case. I mean, you have to define the state from which the inputs are chosen, and only then you can start talking about average case. Otherwise, it makes no sense. Good. Any more questions on this particular, whatever we have done till now? Okay, so let me quickly give you a flavor of a completely different kind of problem. A problem where you don't even know the whole input. Now, excuse me for this pretty hopeless name of the problem. I didn't give the name. Somebody else gave the name. So, and you'll understand why it's called secretary. Okay. So imagine that there is a boss sitting here. Okay, I don't know, a table kind of stuff. A boss is sitting here and interviewing people. And then there are the candidates, C1 to Cn are coming, one after another. Now, the thing is that, I mean, the C1 to Cn comes, that boss interviews a particular candidate. The candidate gets a score, right? Every candidate has a score, S1 to Sn. The score is something that the boss only understands only after that person sees the candidate. Maybe it's like a test that he or she has to give. But the game is that once he sees the candidate, the boss has to either accept or reject her. Meaning, the candidate is going to take a train and go off out of the city if you reject her immediately. Okay, so it's like you interview, you get this code, get to know this code. By the way, the boss doesn't know this code beforehand. The boss, the first when the candidate comes, he sees S1, he decides whether the candidate 1 is getting the job or not. If the boss says, okay, you are getting the job, I like you that much, I give you the job, then the rest of the candidates don't get a job, goes off, game over. But if the boss says that no, I don't want to, then he goes to the next one, and he cannot come back and say that no, I would like the previous one, because by the time the previous one has gone home. Okay? Is the game clear? I mean, it's a nice formulation of the game, but you will understand this is something that is very crucial for all our online transactions and everything that we do nowadays. Goal of the boss is to get the candidate with the best score. Is it possible? No, correct? I mean, not in the worst case for sure. Even in random case, that's not possible. But okay, so now let's try to evaluate the goal of the goal is to pick a candidate whose score is close to the best score. And by close, I mean say half away or 1/4 away or some kind of constant away, let's say. And if the best candidate score is 100, I want to pick someone whose score is at least 25. I don't know what is the best score, by the way. Not that I know that best score. If I knew the best score, then game over. I don't know the best score because I don't know the candidate score. And I have to do that. How do I do it? Yeah, but you are not going back, right? That's a catch here. Say you are seeing the first one may be 100. Okay, first one may be the best one, very much. At the time, you don't know that is the best one. You might think that, oh, maybe the next person is 1,000. So you can reject that candidate. So it's possible that this one is 100 and the rest of them are all 1. You don't know. It's also possible that first one, all of them are 1 and last of them is 100. Are you ready to really go and wait till that point? It's also possible that all of them are 100. I mean, like so many all possibilities are there, right? Nothing can be, there's no guarantee. I mean, it's exactly like buying a TV or computer or whatever stuff. I mean, you are seeing so many laptops or different kind of laptops till now in the world. Should I buy it or not? And maybe the next laptop that you would have seen was the best laptop. You just missed it. I mean, that's exactly what it is. The algorithm is very simple. First of all, randomize these candidates. Okay? I just say, okay, I will pick the candidates at random. Okay? Meaning then first shuffle the candidates. Fine? Once I shuffle the candidates, my algorithm is the following. So at this point it's shuffled, okay? Imagine that these are all shuffled candidates. Meaning anyone have the same probability of coming. I will go up to the half place. So if I have say 1,000 candidates or 100 candidates, I will go to the 50 candidates. I reject all of them blindly. Plain blindly, okay? But I would store this number, max of Si or I equals to 1 to 50. Sorry, not 50, n over 2. So I record the score of the first 50 for first half of the candidates. I am rejecting all of them equally without any chance of accepting. Now, for the next one, so let's call this one to be 8. For the next one, as soon as I see a candidate with a score of more than 8, I take that candidate. So pick the first candidate from n over 2 plus 1 to n with score greater than 8. Okay. Yeah, it's possible that might not get one. In that case, take the last Okay, it seems pretty weird algorithm. The algorithm has some nice properties. What? First of all, whichever is the best candidate, I claim that with probability 1/4, I will pick the best candidate. Best, really the best. Can somebody say why? In this particular case, when do I select the best candidate? When the best candidate, first of all, cannot be in this half, then I don't reject. Right? Best candidate better be in the next half. Now, I can surely pick up the best candidate if the second best candidate is in the first half. Second best candidate in the first half, I have seen that second best candidate score first half. In that case, go ahead. Only one candidate exists who can beat that second best candidate. I pick that candidate. Right? What is the probability of that happening? All the candidates are uniformly distributed. The first candidate going into the second half is probability half. And probability that the second best candidate going in the first half is again probability half. So half times of 1/4. With 1/4 probability, I do pick up this candidate. Quite impressive, right? With some good constant probability, you just pick up the best candidate without knowing anything about who was the best candidate. Okay. And you can prove from here that the expected score is bigger than, actually it will be strictly bigger than, I will write 1/4 of the best. It just follows from basically whatever. Even if I don't pick anyone, or even if I get 0 out of in any other case, but in that 1/4 probability, I am getting the best, right? Expected, on average, I should get 1/4. So this is a class of problems where randomization helps a lot. This is what is known as, there's two names for it, I will write both of them. Online algorithms and streaming algorithms. In both of them, the thing is that you compare yourself with something which is the optimum, which you don't know. That's the first criteria. And secondly, you don't know the whole data. Data is coming as a stream. You can imagine now why it gets applied in computers all the world, all the time, right? Things are moving in a stream. A particular machine sitting in some place is seeing all the possible activities going on, but it's not storing anything. It's seeing as a stream. By looking at the stream, it has to kind of deduce a lot of things. I don't want to go too much into it. This is a completely new topic, but it's one of those areas where, again, randomization just does amazing job. I have 5 minutes. I will say one more thing about randomization, which will basically set my tone for the next half of the talk. I have drawn a big space here. I want you to calculate the area of this space. How will you calculate the area of this? Counting blocks of them, good. Some others. Coming blocks is very similar to what I was going to say. Anyways, let's see. You see it, right? There's some diagram here. Okay, here is a very simple one. You get a monkey. That's the first important thing. Okay. Now, we know the area of this square, rectangle. I don't know, what is it? Maybe, can you guess what is it? 4 feet by 3 feet or something. It's 12 feet. 12 feet is the area of the whole box. Get a monkey now. Give them hundreds of darts. It will start throwing at random all over the place. Right? Say 50 of them, 50 hits the box, hits the whole box. And say 30 hits the inside of this space. Or I just want to look at it. Shaded area. Here is my estimate. My estimate of area is 50 all total 50, or sorry, 30 all total 50, meaning 30 by 50 times the whole area, which is 12. Which is 36 by 5, which is 7.2. That's my estimate. And the estimate is almost as good as you can imagine. But if the monkey keeps on starting throwing more and more and more and more things, if this 50 goes up to 100, my estimate will become easily good. The idea is simple, that it's the area, correct? If you, all I'm assuming is that the monkey is throwing in this space uniformly at random. It is not preferring one side to the other side. It's just throwing randomly. 50 of them has hit here. If you throw it at random, whichever area is big, they should fall with that much probability. But if I split this one right in the middle, half. Half of them you would have expected to fall here, half of them would have expected to fall here. Why? Because it was right in the half, right? Meaning half of the area. Similarly, if I had cut out a half an area here, perfect half area here, you also have to expect the same thing. Right? A random sampling, meaning you randomly sample points. Of course, how do you random sample points? Here we are throwing dirt. Randomly sample points from this whole box, you get an estimate of this area. This is extremely, this is actually the simple concept of estimating area or approximating volume, or which will come to the next step of approximation algorithms of problems of objects, of numbers in